tool you can use to resolve vectors into their x-ness and their y-ness is a simple process called the parallelogram method. And this relies on the fact that you can put a box around any vector that isn't necessarily on the x or the y. Now, I use a special paper called Cornell note-taking paper, and I've provided a link on my portal page, which I'm about to show you where to go find it. But in reality, you can use any graph paper that you want. So this is my portal page, and if you go into laboratory physics, you will see my homework assignment, but we're looking for shared documents over here. We're looking for a file called Cornell Cartesian Graph Paper. If you simply save this and then print it, you'll have the paper that I'm working on. So the parallelogram method is pretty good at resolving some fairly easy scenarios. For example, like this. What happens when forces are applied in two directions at once? So for example, if I had a small sailboat and it's being pushed with 8 newtons up and 12 newtons to the right, what direction does the sailboat actually go? Now I have my Cornell paper, but in reality, if you understand that 8 newtons up is going to push it up, and 12 newtons is going to push it to the right, can you see that I'm only going to be concerned with the first quadrant here? I really don't care what happens in the second, third, and fourth, and so I'm just going to focus on the first quadrant here. So I'm going to draw some axes. Now, I've already drawn my 8 newtons up, which I've put in blue because that's in the y-axis, and my 12 newtons to the right, which is in red because that's traditionally in the x-axis. But if you'll recall from your free body diagram work, it really doesn't matter where I draw this vector. I could draw it here, but I could just as well draw it right here as well. It means the same thing. And in my y-axis, I could draw it along the axis, or I could draw it here as well. And you'll get this very interesting shape, this rectangle, which is also known as a parallelogram. And that's where the parallelogram method gets its name. Now, if I simply draw my resultant vector from the origin to where my two vectors meet, that is called the resultant vector, and this is the parallelogram method. Once you have that resultant vector, you can take a measuring device and measure from the origin to where my two vectors meet, transfer that length into the x-axis, and simply count up the number of boxes, and that tells me the magnitude of my force. The parallelogram method requires that you draw your vectors very, very accurately, because how accurate you draw them really dictates how good this measurement line is, and that you draw a resultant vector and you measure the length. Alright, let's try softball, except in this case I'm not going to use colors. I'm simply going to pretend that I simply have a pencil in order to resolve x and y, and you'll notice that I paid special attention to describe the y-axis layer, and also the x-axis. You see this little subscript that tells me this is the force in the x-axis? So when I actually go to put these vectors in my Cartesian coordinates, I can specify that the force in the y-axis with this little subscript y, and I have a force in the x-axis with this little subscript x. Now traditionally I'd use an arrow to draw a red line in that direction and a blue line in that direction. But since I have the subscripts, I'm telling my audience. So if I were to draw 10 newtons in that direction, draw a force 10 boxes long, and 4 newtons in that direction, 4 boxes long, and then transfer my imaginary vector to the other side, transfer my imaginary vector to the other side, draw the resultant vector, transfer the measurement down, and I can measure the length and say it's about 10.5 newtons.